Hello everyone, this is Mr. Motugi in our today's class for mechanics of machine. And our today's lesson we are going to look at moments of inertia or second moment of area of our symmetrical sections. And a good example of a symmetrical section is an I section of a beam. What we mean by basically by a symmetrical section is a section who's considering a certain axis, as you can see here, considering a certain axis, for example the neutral axis, the upper section of the upper portion of the beam and the lower section of the portion of the beam are actually similar. An I section of a beam, as we have here, is one example of a symmetrical section of a beam. Going direct to the calculation, but before that we are going to look at the various parts of the section, the various parts of the I-beam section. An I-beam section usually composes of two parts, that is the flange and the web. The flange is the part to which the load lies, whereas the web is the supporting or the vertical section of the beam. Going direct to the calculation of the moments of inertia, as we are going to see, we are going to divide or to consider the section into three rectangles. That is rectangle A covering the whole area, and rectangle B and C, which are the cuts from the rectangle A to resulting to the section. The moments of inertia of a rectangular section is given by the formula BD cubed over 12, where B is the base of the section, that is the rectangular section, and D is the thickness of the section. Like for example, considering rectangle A, the base is 100, whereas the thickness is 120. Going direct to the calculation of the moments of inertia of the section, we can see that dividing the section into three rectangles, that is rectangle A, rectangle B, and rectangle C, the moments of inertia, or the area moments of inertia of the section will be given by the moments of inertia of rectangle A, subtract the moments of inertia of rectangle C, and and then you subtract the moments of inertia of rectangle C. That is the whole rectangle, you subtract the rectangle B and C. Direct to the formula, that is calculating the moments of inertia of rectangle A. As we can see, the base is actually 100. That is, this is 100. Whereas the thickness of the section is actually 120, as can be seen from the diagram. That is the moment of inertia of rectangle A. You can see that rectangle A is actually symmetrical about the neutral axis. In the same way as rectangle B, this one is symmetrical about the neutral axis. And rectangle C is actually also symmetrical about the neutral axis. So it would be actually correct to say that the moments of inertia of the section will be given by the deduction of moments of inertia of B and C from moments of inertia of rectangle A. Coming direct to the other part of the rectangles, that is rectangle B and C, as you can see that rectangle B and C are actually similar from the diagram, and the moments of inertia of both rectangles will actually be similar. That is, considering, for example, the base of rectangle B and C. The base of rectangle B will actually be given by 100, subtract the thickness of the web. The thickness of the web is 10 millimeters. That is 90 divided by 2, because you have rectangle B and C. That is 45 millimeters. And the height of the rectangle is actually given by 120. That is the thickness of rectangle A. You subtract the flange thickness, that is 20 millimeters, and the lower flange thickness, this is also 20 millimeters. So it's actually 80. So BD cubed over 12, that is actually 45. You multiply by 80 cubed, and then you divide by 12, giving you the 1,920,000. The units for moments of inertia is actually in millimeter raised power 4. You can convert it into meters per 4, but most preferred unit is millimeters per 4. For the I section, as we have seen, the I section moments of inertia or second moment of area will be given by the moments of inertia of rectangle A, subtract the moments of inertia of rectangle B and C. But the moments of inertia of rectangle B and C, they are equal. So it's actually like you're multiplying the moments of inertia of rectangle B or C twice the moments of inertia of rectangle B or C, resulting to the answer that we have here, that is 10,560,000 millimeters raised to power 4. Basically, what is the essence of calculating the moments of inertia of a section? Most beams, these are the kind of beams that we have in most practical applications that we have around, and they are subjected to loading. That is, they carry different loads in areas that they have been applied. And that means that the moments of inertia in this case helps us to determine the resistance, or possibly we can say the maximum stress that the beam can be subjected to, that it can be able to handle. We are going to see that in another section. An I-beam section. Where do we find an I-beam section in any application in real world, in real life? They are basically like everywhere. If we go to structural works, things like beams, columns, this is where we find the sections. These are actually the sections that make up the beams. We also find them in most cases like machine frames. Things like automotive frames. They are actually everywhere. So as we can see that the section is actually symmetrical. There are other sections that you'll find out there that are actually not symmetrical. That is, if it's not an I-beam section, it could be a T-beam section. That is what we're going to look in our next class. And for today, we are actually going to reach there for our class. In our next lesson, we are actually going to look at the asymmetrical sections that we have around, we are actually going to, that we have around in most structural works, or in any other work that is related to engineering. Thank you for today's. Ensure you're keeping safe. Ensure you wear the mask. Ensure you wash your hands, and ensure you're safe. Thank you.